Okay, let's unpack this. What if everything you thought you knew about geometry, those perfectly straight lines, those neat triangles from school, what if that was just like one piece of a much bigger, maybe wilder puzzle? For centuries, we've built our world on these seemingly simple truths, right? But what if there were other imaginary geometries that have profoundly shaped how we see the universe, how we navigate, even the buildings and art right around us?
That's exactly what we're diving into today. Our mission in this deep dive really is to explore this revolutionary world of non-Euclidean geometries.
Okay.
We'll get into their controversial beginnings, the brilliant minds who dared to challenge thousands of years of wisdom,
Right.
and look at their surprising real-world applications. Everything from theoretical physics to architecture and art. We've gathered sources from dense math texts, sure, but also historical accounts, architectural analyses.
So giving it the full picture, basically.
Trying to, a shortcut to getting informed on this really fascinating topic.
Great. So let's start with the familiar then. Most people, when they think geometry, they're thinking Euclid. Flat planes, lines going straight forever, triangles where the angles always add up to exactly 180 degrees. It's the common sense geometry we use.
Yeah, the one that tells us parallel lines just, well, never meet.
Exactly.
And that common sense, it really comes down to Euclid's 5 axioms. They were the foundation, the bedrock for like 2,000 years, considered absolute truth.
But there was a catch.
There was a catch, and here's where it gets interesting. The 5th axiom, it's often called the parallel postulate. And it became this huge point of frustration.
Why is that?
Well, for 2 millennia, mathematicians really tried and failed to prove this 5th one using just the other 4.
Oh, okay.
And this constant failure started to whisper a revolutionary idea. What if it wasn't dependent on them? What if maybe it could actually false?
And then, like often happens in science, things get dramatic.
Yeah.
Tell us about the people who actually dared to question that 2,000-year-old idea.
Right. Here's where we meet some truly unsung heroes. Nikolai Lobachevsky and Janos Bolyai.
Okay.
Working independently, early 19th century, they just dared to challenge this ancient teaching. Lobachevsky especially, he showed you could build a whole consistent mathematical system where Euclid's 5th axiom wasn't true.
Wow. So what did that world look like?
He called it imaginary geometry, and in it, concepts like similar triangles, they just wouldn't exist. Same for rectangles as we know them.
Wait, hold on. No similar triangles.
Oh, rectangles.
Rectangles. That's really hard to wrap your head around if you're used to Euclid. How does that even work? Like, what does it mean for the shape of things?
It means, basically, if you scaled up a triangle in this imaginary space, its angles would change. They wouldn't stay the same like they do on a flat plane. Every triangle size has its own angles. Yeah. But the academic world, they were absolutely not ready for this. Lobachevsky was relentlessly criticized, mocked, rejected. Oh, yeah. His ideas were called shamelessness of false new inventions. And his fate, well, it was pretty tragic. Fired from the university, lost a child, went blind, died poor.
Oh, that's awful.
It is. Even Gauss, the famous mathematician, he recognized Lobachevsky's work was brilliant, apparently quite like his own unpublished ideas, but he was afraid of the criticism. He never backed him publicly. And Janos Bolyai's father, Wolfgang, he wrote about his son's efforts, ending with a broken mast and torn sail. It just shows the huge struggle, the isolation they faced.
Hearing about Lobachevsky really makes you think, how many crazy ideas today might just be ahead of their time? It's almost a warning to keep an open mind, isn't it?
It's a powerful reminder, definitely.
So, okay, let's try and visualize this then. What exactly is non-Euclidean geometry if it breaks these rules we know so well?
Right, visualization is key. Let's start with something maybe easier to grasp. Spherical geometry. Think about drawing lines on a sphere, like the Earth.
Okay, like longitude lines.
Exactly. Those straight lines on a sphere are actually great circles, the shortest path between 2 points. If you draw 2 of them starting parallel at the equator,
They meet at the poles.
That's totally different from flat geometry, and triangles are different too. Imagine a triangle. North Pole down to the equator, go along the equator for a quarter turn, then back up to the pole.
Okay.
That triangle has 2 90-degree angles at the equator, plus whatever angle is at the pole, let's say 50 degrees. So 90 plus 90 plus 50.
That's 230 degrees, way more than 180.
Exactly. That's a surface with positive curvature. And spherical geometry isn't just theoretical, it's fundamental for navigation theory, how we plot courses across our curved planet.
Okay, so that's positive curvature, parallel lines meeting. What about the opposite?
Right, that brings us to hyperbolic geometry. This describes surfaces with negative curvature. Think of a saddle shape, maybe?
Like a Pringle chip. Kinda.
Sort of like that, yeah. In this geometry, triangles have angle sums less than 180 degrees.
Less.
And here's maybe the weirdest part. From a single point, you can draw an unlimited number of parallel lines to another given line, or geodesic, on that surface.
Unlimited parallels. Wow. Okay, that is counterintuitive.
Definitely.
So these abstract, even imaginary worlds, they seem really theoretical, but connecting this to the bigger picture, are they just math games or do they actually describe reality? And maybe a simpler question first. For everyday stuff like building my house or drawing a map of my street, Euclidean is still fine, right? These other ones are more for the big stuff.
You've hit a really critical point there. Yes, absolutely. For local, everyday things, building, mapping your neighborhood, Euclidean geometry works perfectly. It's a fantastic approximation.
Okay, good.
But when you zoom out, look at the grand scale, the universe itself, these imaginary geometries become essential.
How so?
Well, when Einstein was developing his theory of relativity, figuring out the structure of space-time, he needed non-Euclidean geometry. It turns out gravity curves, space-time, and Euclidean geometry just doesn't cut it on that cosmic scale. Our modern understanding of astronomy, cosmology, space exploration, none of it would exist without these non-Euclidean frameworks.
So those crazy dreamers, like Lobachevsky and Bolyai.
They actually laid the mathematical groundwork for us to understand the cosmos and even travel beyond Earth. It's quite incredible.
That's incredible. It really is. And beyond the cosmos, you're saying these ideas, these geometries, literally shaped our built world too. Cathedrals, skyscrapers.
Absolutely. It's amazing, isn't it? If these concepts describe the universe's curvature, maybe it makes sense that humans, especially artists and architects, would start exploring similar ideas, consciously or not.
So how did that play out historically?
Well, the link between geometry and architecture is ancient. Euclidean geometry, flat planes, right angles, that was the basis for styles from antiquity right through the Romanesque period. Think regularity, orthogonal forms.
Right, solid, stable-looking stuff.
Exactly. Then things started shifting. From the Gothic period through the Renaissance into the Baroque and Neoclassical eras, perspective and something called projective geometry became super important.
Projective geometry. How's that different?
Unlike Euclidean, which focuses on fixed shapes and sizes, projective geometry looks at how shapes transform when projected onto different surfaces. It's the math behind creating realistic perspective and sometimes amazing illusions.
Like those paintings that look deep.
Precisely. Or think of Bramante's work in Milan, the St. Mary by St. Cyturus Church. He created this illusion of a huge, deep, barrel-vaulted apse.
Yeah.
But the actual physical depth was only 97 centimeters, less than a meter. Pure geometric skill creating that monumental feeling.
Wow, okay. That's clever.
And then you get to the Baroque era, late 17th century. They went all in on transformation. They actively sought free and open surfaces, elliptical and in constant transformation. It was like they were reflecting this new mathematical understanding that space wasn't rigidly flat.
So curves and dynamism.
Exactly. Think of Guarini in Turin, the Chapel of the Holy Shroud, San Lorenzo Church. He masterfully mixes convex and concave surfaces, sculpting these really dynamic, flowing spaces. It really challenges that fixed Euclidean viewpoint.
And was he aware of the math?
Oh, yes. Guarini studied infinitesimal calculus, the math of curves and change that directly fed into his ability to manipulate space in these new ways.
Fascinating. So fast forward to modern times. How do non-Euclidean ideas show up?
They're kind of fundamental to modern architecture and art, really. You see artists like Picasso, Malevich, breaking objects apart, reassembling them, showing them from multiple viewpoints at once. It's like they're exploring space beyond the standard 3 dimensions, much like non-Euclidean geometry allows different perspectives on space itself.
Cubism, right? Seeing all sides at once.
Exactly. And in architecture, you had movements like constructivism and deconstructivism. They embraced industrial materials, shapes derived from, technical processes. They deliberately broke the old rules of composition, echoing that departure from Euclidean norms.
Any famous examples?
Sure, the Zhukov Tower in Moscow is a great one, this beautiful hyperboloid structure. Or Vladimir Tatlin's projected tower for the Third International. It was never built. But the design was radically non-Euclidean, this spiraling, dynamic form. Ultimately, Einstein's theory of relativity tells us that Euclidean, hyperbolic, and elliptic geometries can all be successfully used to describe different aspects of our universe. It just shows how interconnected these seemingly imaginary worlds are with our physical reality and the spaces we build.
So we've really covered some ground here, from abstract math problems and personal tragedies,
Yeah.
all the way to understanding the universe and shaping the buildings we live and work in. It's kind of mind-blowing, isn't it? How challenging just one assumption could lead to so much change.
It really is.
As we wrap up, what's the big takeaway for us, listening to this? What should we be thinking about?
I think the story of non-Euclidean geometry is a powerful reminder. It shows that ideas which seem, well, ridiculous or even repugnant to one generation might actually be laying the foundation for the next huge leap, the next scientific or artistic revolution. It really encourages us to consider the power of challenging what seems obviously true. And that raises a big question, maybe the final thought for you to chew on. What other imaginary or unconventional ideas are out there today? Ideas that maybe seem outlandish, maybe face backlash right now?
But could be the future.
Exactly. Could they be setting the stage for the next breakthroughs in how we understand things, how we create things? It's worth keeping an eye out because the future often looks a lot like yesterday's impossible dream.